Welcome to this video on sampling distributions, chapter 9 in our book, and this is where the power of statistics really comes through, and then we can start to prove and infer measurements based on the power of chapter 9. So first we're going to go through some vocabulary, just a little review to remind you, so when I use the words, you know what I'm talking about. Parameter, that is the measurement of the population that you're interested in, and it uses Greek letters like mu or sigma. Uh, Rho technically is used for the percentage parameter, but a lot of times we just use P because it's easier to write and it looks the same. Just an example, if I took all the IQs of all Americans and took the mean of those, that would be the population mean if my population was just Americans. A statistic is a sample because often we can't get the population. It's just not practical to be sampling population, to be studying populations, so we sample the populations. Uh, and those we use non-Greek letters like X bar for mean, P hat for proportions, and some examples like if I just did 500 Americans, found their IQs, and found the mean, that would be X bar, not mu. Or instead of P, I would use P hat if I found like 200 women, only 40 like broccoli. Uh, and then just a side note that we'll get into more when we get into later chapters, but the population needs to be 10 times as big as your sample because you're not sampling with replacement, so it can mess up the proportions if your sample is too large of a proportion of your population. All right, a couple of things when we're sampling. We want a sample that has low bias. So if it's biased, it's not a good predictor of whatever parameter you're measuring. So like if you're doing means, it means the mean is not really close in your sample to what the actual population mean is. So you want low bias. And in the visual here, so this would be a bias predictor, this blue one. And the black one would be the unbiased predictor if this line were indeed the population parameter, because the black line is centered around that population parameter, whereas the blue one, it is off to the left, so that would be a bias predictor. Another nice example of this concept is the bullseye. So in A, if the bullseye is what we're trying to get to, this is in the middle, then this in A, we're biased because we are not near the bullseye, but we don't have much variability, which is good, but we're biased from the actual population. B, all the shots are centered around the bullseye, so it has low bias, but it's highly variable. Then C has high bias and high variability, which is not good. And then D is what we always want in our samples, to have low variability and low bias, so they're all centered, grouped around the bullseye. All right. So now comes the question, what is a sampling distribution? So a sampling distribution is the distribution of a statistic is all the possible values of that statistic of the same sample size. So for example, if I wanted the mean IQs of Americans, the sampling distribution of those means would be all the possible samples of, let's say, size 100. I sample 100 people. So it's all possible samples of size 100 for that population. And it's a little easier to understand if you see the visual. So if I have this group of people all look like they dress for work, and I'm sampling their IQs, we'll say, then I average them. Then I take another sample, I average that. I take a different sample, I average that. All the possible samples, all the possible combinations of the same size sample, you will end up getting a sample that looks approximately normal there, and that's your sampling distribution. All right. And this is the all-powerful theorem that a lot of statistics is based on, is the central limit theorem. And so what it says is as you take more and more samples of the same size, the distribution will get closer and closer to a normal curve that is centered around the true population mean. So it will be an unbiased predictor and it has a known distribution. It'll be approximately normal, so we can use all our z-scores and all the things we know about the probability of being at a certain place in the normal distribution. And then at the end, the means of your sampling distribution will be the same as the population, and the standard deviation of your sampling distribution is the standard deviation of the population divided by the square root of your sample size. Now the question becomes, how large a sample do you have to take for this to be true? So before we go through these notes, let me show you on a nice little app, this sampling distribution app, where you can play around with things. So let's start off with a skewed distribution. So this top graph is our parent population. And I'm going to let's start with a low sample size. Let's do just 2 things. So if I animate, I take a sample of 2 data points from that population and take the mean. Then I can do it again, take the mean. Now, we don't want to watch this over and over again, but let's say I take 10,000 samples. So I took 2 data points from my parent population, found the mean, and then in the blue is if I did that 10,000 times. You'll notice this is still skewed like the population, which is not what we want. We want something to be approximately normal. So let's change this and let's go up to 10. So this time I would be taking 10 data points, taking the mean and putting that in my sampling distribution. And then you could do it again. All right, so we don't want to watch that. So 10,000, even at size n equals 10, this is getting close to approximately normal. There is a little bit of a tail still, but if we go up to a sample size of 25, so we take 25 data points, we'll only watch this once because it'll take a while. Take 25 data points, take the mean of those, and if we did that 10,000 times, this is very close to approximately normal. And over here you can see the mean. It's close, it's almost exactly what the mean of the population is. And the standard deviation, if you were to divide 5.22 by 5, that's going to be close to that standard deviation we have there. All right, so let's go back and just finish up this PowerPoint. All right, so the question goes, how big does your sample size have to fit to fall into the central limit theorem? Most books say a sample size of 30 is needed, no matter if you don't know the shape of your population. Now, if you know the shape of your population starts off approximately normal, then it doesn't matter the sample size. But if you have an unknown population, a skewed population, a uniform population, a sample size of 30 will pretty much guarantee that you can use the central limit theorem to say your sampling distribution will look approximately normal. And so here's a little visual here. So normal distribution, here's our sample sizes. So here we get sample size of 30, sample size of 2. So uniform, once you get to 30, it looks approximately normal, skewed, and then just anything. By the time you get to a sample size of 30, the sampling distribution looks approximately normal. And that's because it's averaging out those extreme values, and you're more likely to get a cluster of values near the mean of the population. And that's why the central limit theorem works. So the keys of it are that the mean of the population is going to be the same as the mean of your sampling distribution. And I'm doing the mu of subscript x bar, that's kind of how they denote the mean of the sampling distribution, because it's the mean of your x bars. And the standard deviation of your sampling distribution is equal to the standard deviation of the population over the square root of your sample size. And there's a little things that we do with that later in some later chapters that will fudge that a little, since generally we don't know that number either. And then the larger the sample size, the smaller your standard deviation becomes, because you're dividing by the square root of your sample size. All right, I hope this helps a little bit understand central limit theorem, and we'll do some activities to get this more in your head during class.